Physical Chemistry, Chapter 19, Section 6. Now we'll talk about the helium atom and the Pauli principle. So here's a helium atom. Here we have, inside the nucleus, we have Z times E, the electron charge, times the atomic number. So we have one electron over here, one electron over here at any one time. So the distance from the nucleus to this first electron is R1, and the distance from the nucleus to this other electron would be R2, and the distance between the two electrons is R1 to 2. So, like I said, in the nucleus, we've got two protons, so we have 2e in the nucleus. So we have to remember about three potentials, R1, R2, and R12. So the Hamiltonian is going to be equal to minus h bar squared over 2me. But now remember, this would actually be the reduced mass, but that's a close enough approximation. Del 1 squared minus h bar squared over 2me. So this is for electron 1, electron 2, that's del 2 squared. Minus z times e prime squared over r1 minus z times e prime squared over r2 plus e prime squared over r12. Notice there's no z over here because it's just the two electrons, not the nucleus. Now, minus h bar squared over 2me times del 1 squared, that's the kinetic energy the electron 1 has. And then minus h bar squared over 2me times del 2 squared, that's the amount of kinetic energy the electron 2 has. And then the rest of these terms, minus z e prime 1 e prime squared over r1 minus z e prime squared over r2 and plus e prime squared over r12, that is the potential energy of the electrons. Now remember, positive potential energy means they're repelling each other. Obviously this term is positive because the two electrons repel each other. Negative potential energy means their attraction. So the nucleus is attracting electron 1 and the nucleus is attracting electron 2. Now because of R12, we can't separate variables, namely the two electrons. We can't look at them separately. So we can't just get an exact answer. So we have to use approximation methods. So R1, of course, is going to be the square root of x1 squared plus y1 squared plus z1 squared. Hamiltonian of psi is equal to energy times psi. But we have to use the psi for a helium atom, not for a hydrogen atom. So psi is going to be a function of x1, y1, z1, x2, y2, z2. So it's going to be a function of spatial coordinates only. So obviously we're talking about time independent. Now, we can do that in spherical coordinates instead and say psi is a function of r1, theta 1, phi 1, and r2, theta 1, phi 2. Now, we're going to ignore the e prime squared over r12 to simplify. So we get the Hamiltonian is just going to be equal to Hamiltonian for electron 1 plus the Hamiltonian for electron 2. So we're assuming the electrons don't interact, which is obviously wrong because they repel, but one thing at a time. So we get, for electron 1, the Hamiltonian is going to be equal to minus h bar squared over 2me times del 1 squared minus z e prime squared over r1. And then for the Hamiltonian for electron 2 is going to be equal to minus h bar squared over 2me times del 2 squared minus z e prime squared over r2. Now these can be solved to have an exact answer. So here's the equations. Hamiltonian 1 of psi 1 is equal to energy for electron 1 times psi 1. And the Hamiltonian 2 of psi 2 is equal to energy of electron 2 times psi 2. And then our Hamiltonian approximate is just going to be H1, Hamiltonian 1 plus 2. So for a hydrogen atom, to approximate each electron is one atom in one atom. So E1 is going to be equal to minus z squared over n squared times 13.6 electron volts. So for helium, z equals 2. So z squared is equal to 4. So energy level 1 is minus 4 over 1 times 13.6 electron volts. That's minus 54.4 electron volts. And energy 2 is equal to energy level 1, which is equal to minus 54.4 electron volts. So by that, the total energy would be just E total, which is E1 plus E2. That's minus 54.4 electron volts plus minus 54.4 electron volts. So we get minus negative 108.8 electron volts. And of course we can't find that experimentally. So we go helium, going to helium plus an electron. That's the first ionization energy. We actually get the ionization energy first is 24.6 electron volts. And then going from helium plus ion to helium 2 plus ion by removing an electron, obviously, that's the second ionization energy. The second ionization energy, that is 54.4 electron volts. So the total of the two is only 79.0 electron volts. So the ground state energy for helium is minus 79.0 electron volts. So the error is, again, we got the estimated value of 108.8 electron volts minus the actual value of 79.0 electron volts divided by 79.0 electron volts times 100%, we get 38%, which is obviously a huge error. So we can't solve it exactly with the E prime squared over R12 term. So again, we can use approximation methods like the perturbation method. So GS is, remember, is ground state, and APP is going to be approximate. So we have the psi GS approximate is roughly equal to Z over A0 to the 3 halves times pi to the minus 1 half times E to the minus Z R1 over A0 times Z over A0 to the 3 halves times pi to the minus 1 half times E to the minus Z R2 over A0. This is R1, R2. So Z is equal to 2 for helium. Now this is only for non-interacting particles because they're multiplying, like their independent probability. So the energy for the ground state is equal to the integral of psi for the ground state, the complex conjugate, times the Hamiltonian of psi gs d tau. And Z is roughly equal to zeta. Zeta is a refinable parameter. We're going to say that's the effective nuclear charge. So the Hamiltonian is psi is ground state approximate is roughly equal to energy ground state, psi in the ground state. So psi in the ground state is roughly equal to 1s1, 1s2. So that's two wave functions multiplied together. But that's without spin. So a better notation actually 1s2. So helium is 1s2. Save is 1s1 and 1s2. So the two electron spin functions, so we have probabilities. Alpha is up, beta is down. So we have alpha 1, 2, alpha 2, beta 1, beta 2. That's a good term because those are both symmetric. But then we have alpha 1, beta 2, and beta 1, alpha 2. These are bad because doing that you can tell which electron is which. And electrons are all the same. Electrons are indistinguishable, so the bottom row doesn't make any sense. So we're going to take the normalized linear combination of the bottom two. So we have 1 over the square root of 2 times alpha of 1, beta of 2 plus beta 1, alpha 2. That's symmetric. And then we have 1 over the square root of 2, alpha 1, beta 2 minus beta 1, alpha 2. That's anti-symmetric. And then we have 1 over the square root of 2, alpha 1, beta 2 minus beta 1, alpha 2. We'll say that's equal to A. And then we're going to swap electrons, and we'll get 1 over the square root of 2 alpha 2 beta 1 minus beta 2 alpha 1. That's equal to minus 1 over the square root of 2 beta 2 alpha 1 minus alpha 2 beta 1. That's equal to minus A. So what is interesting, if you swap the electrons, it reverses the sign. That's what anti-symmetric means. Now let's talk about the Pauli principle. A fermion is a particle with half integral spin. So like lowercase s, 1 half, 3 halves, 5 halves, etc. So examples would be protons, neutrons, electrons, atomic nuclei, etc. A boson is a particle with an integral spin, like 0, 1, 2, 3. An example would be a photon. So the Pauli principle says when two identical particles are interchanged, the total waveform, that means spatial and spin, changes to minus psi. In other words, it's anti-symmetric if they are fermions, but to positive psi, symmetric if they are bosons. So, approximate ground state spatial function, 1s1, 1s2 for helium, that's symmetric. So we have psi ground state is roughly equal to 1s1, 1s2. This part's symmetric, but then 1 over square root of 2, alpha 1, beta 2 minus beta 1, alpha 2, that's antisymmetric. And that's 1s. That's the same as up, down. Okay, so we can also write that using determinants instead. So we have psi of ground state is roughly equal to 1 over the square root of 2 times this whole determinant. We have 1s1 alpha 1 over 1s2 alpha 2, 1s1 beta 1, 1s2 beta 2. So remember the determinant of A, B, C, D is AD minus BC. That's from linear algebra. So for helium, we have 1s2, that's the ground state. So for helium, the first excited state is any of these. It could be 1s1, 2s2, 1s2, 2s1, 1s1, 2px2, 1s2, 2px1, 1s1, 2py2, 1s2, 2py1, 1s1, 2pz2, or 1s2, pz1. Now, these are actually a problem then, because they distinguish electrons. Remember we said electrons are uninterchangeable. So if you have a formula that can tell them apart, your formula is wrong. We need to use linear combinations instead. So instead we get psi 1 is equal to 1 over the square root of 2 of 1s1, 2s2 plus 1s1, 2s1. Or psi 2 is equal to 1 over the square root of 2, 1s1, 2s2 minus 1s2, 2s1. And psi 3 is equal to 1 over the square root of 2, 1s1, 2px2 plus 1s2, 2px1. And then psi 4 is equal to 1 over the square root of 2, 1s1, 2px2 minus 1s2, 2px1. Or psi 5 is equal to 1 over the square root of 2, 1s1, 2py2, 1s2, 2py1. Or psi 6, 1 over the square root of 2, 1s1, 2py2 minus 1s2, 2py1. Or psi 7, 1 over the square root of 2, 1s1, 2pz2, 1s2, 2pz1. Or psi 8, 1 over the square root of 2, 1s1, 2pz2 minus 1s2, 2pz2. So that's 8 different wave functions. So we're going to say E sub k is the energy of state k. So we have the Hamiltonian of psi of k is equal to energy of state k times psi of k. The energy of k is the integral of psi of k star times the Hamiltonian times of the psi of k d tau. That's going to be equal to integral of psi, the complex conjugate of psi of k times energy of k times psi of k d tau. And that's equal to energy of k times the integral of complex conjugate of psi of k d tau, or just the energy of k. Now remember, the integral of psi star k, psi k d tau, that's normalized, so it's equal to 1. So let's talk about an s orbital. So we have a 1s, 2s. So the 1s, that's what we call singlet. There's no degeneracy. There's 1 over square root of 2, 1s1, 2s2 plus 1s2, 2s1. That's symmetric. That goes with alpha 1, beta 2 minus beta 1, alpha 2, 1 over square root of 2. Then there's the 3s state. That's triplet or threefold degenerate. There's minus 1 over 2, 1s1, 2s2 minus 1s2, 2s1. That's antisymmetric. And that goes with alpha 1, alpha 2, or alpha 1, beta 2 plus alpha 2, beta 1, 1 over square root of 2, beta 1, beta 2. And then for the 1s, 2p, then here's 1p, that's 1 over the square root of 2, 1s1, 2px2 plus 1s2, 2px1. Or 3p, that's 1 over square root of 2, 1s1, 2px minus 1s2, 2px1. Then we have the integral of psi star k, Hamiltonian psi k d tau, that's equal to energy of state k. So instead of energy levels, we call them terms, or term symbols. So like this 1s and 3p, those are terms. If you have multi-electron atoms, 2p is the higher energy state than 2s. Now spin functions for 3p are alpha 1, alpha 2, alpha 1, beta 2 plus alpha 2, beta 1 times 1 over the square root of 2, or beta 1, beta 2. These are each symmetric, and the 3p spatial function is antisymmetric. So the wave spin function overall is antisymmetric, like it should be for a fermion, such as an electron. But that's 9-way degenerate, 3 for x, 3 for y, and 3 for z. Likewise, 1p is 3-way degenerate. See handout figures 85 to 88.